For today's lesson, we're going to be doing more dynamic programming. We're going to be wrapping up dynamic programming for today. So in last week's lesson, I introduced the fundamentals of dynamic programming, as well as I showed some examples. I also mentioned some of the basic dynamic programming questions last week. For today's lesson, we'll actually cover those questions in detail, since I kind of gave you a brief description and just said, okay, I'll cover them next week. And I will go back. I'm a man of my word. I'll go back and cover those questions. This will also be the very last lesson that I'll be preparing you for. That will prepare you for the CCC. I won't be posting. I won't be posting any more. Comparative programming questions. So the first question we're going to be covering, we're going to be covering the same questions in the same order. And so for today, the first question I posted I talked about in last week's lesson was longest common subsequence. So as stated in my previous lesson, the longest common subsequence is just to find the length of the subsequence from two sequences that both it's to find the length of the subsequence from two sequences that both exist in the two sequences. Might be a mouthful, but I can explain a bit more. All right. So let's start with an approach. Let's use the sample case from the longest common subsequence problem on DMOSH. So let's say we're given the following 1, 4, 3, 4, 2, 2, 1, 3. All right. So if I look at this question, so 1, 4. Let me move myself. 1, 4, 3, 4, 2, 2, 1, 3. All right. If we look at this question, we can see that the longest common subsequence in this is 1 and 3, since there's a 1. So in here, whoops. On the first, we can look at the second subsequence. All right. The only subsequence you can make is like 2, 1, 3, 2, 1, 2, 3, 1, 3, and like each individual number. All right. While the other subsequence, you can we can have a subsequence of 2 on both, a common subsequence of 2, right? We can have a common sequence of 1 as well, and we can have a common subsequence of 3. But the longest one is 2, 1, 3. No, it's 1, 3. There is no 2, 1, 3. If we had 2 up front, like here, then maybe we can have a longest common subsequence of 2, 1, 3. But in this case, the longest common subsequence here is just 1, 3. All right. And a subsequence is pretty much just any combination of letters or numbers from this original sequence. So like, let's say we had like A, B, C, D, E, F, G. All right. And the longest, like, we can have a subsequence of A, B. So A, B, C. We can have A, B, D, A, F, G. It doesn't matter if we remove or add letters. It just has to follow the same order. So it has to be like in the exact same order as it's presented. So you can't have B, A, C, or like D, C, G, or like D, A, G, or something like that. That's not allowed. You can't have that. That's not a subsequence. So what we're trying to find here is a subsequence that exists in both sequences, and it's the longest one that we know so far. So how do we approach this problem? All right. Well, you need to find the longest common subsequence from the start of one sequence to some given point. So like going back to like this first two subsequences here, right? So like these two here. If I can draw a bit better, these two here, all right? We just start from this point. So like, let's say we start from 1 and we just go to, we go to like some random point. We only look at like the first letter, the first 2 letters, the first 3 letters, the first 4 letters, the first 5 letters, and we find whatever subsequences in that, and we compare it to the subsequences in the first letter of the second sequence, the first 2 letters of the second sequence, the first 3 letters of the subsequence, the second sequence, and we just try to find common subsequences in that point. This means we need to create a 2D list to keep track of the longest common subsequence between the 2 sequences and each sequence we make from there. So you also need to have to keep track. To keep track of having a sequence of 0. So if we start with nothing, you know, that means the longest common subsequence from having a sequence of 0 is 0. You can't create a subsequence with nothing. So you know that it's 0. So that means the 2D list needs to be the sequence 1 length plus 1, since we're taking nothing, and by the sequence 2 length plus 1, right? So let's create this subsequence, all right, with this question. Let's create this 2D array. So 2D list. So if I create, whoops, I can't draw. So if I create this, or actually I created it in the future, right? So now to approach this problem, okay, let's say, okay, if you have an empty sequence, you can't make a common subsequence. So you can instantly say the common subsequence between an empty sequence, between one sequence and an empty sequence, or between two empty sequences is 0. Otherwise, when we initialize the 2D list, we can every other value is just some unknown value. We can just say let's just say it's -1. So I'm giving it the value -1, since you can't have a subsequence of -1 if you have some value, right? The lowest value you can have for a common subsequence is 0, in which you just take nothing. You can't have -1. You can't just be giving more. That doesn't really fit in with the question. So each row and column corresponds to the length of the longest common subsequence up to a given point on one sequence, and up another given point on this other subsequence. So it's like, so let's say we have the coordinates x and y on this 2D list, right? So up to the point of x and y on the 2D list corresponds to the common subsequence between sequence 1 starting at 0 to x, and the common subsequence from sequence 2 starting from 0 to y. All right, sounds a bit complicated. Let's just initialize this 2D list. All right, so if I just copy this over and just increase the size so I can easily work on it, we have this 2D 2D list, right? Now we have this 2D list. So I have the empty part, so set to 0. Since if we take nothing, that means we can't have a common subsequence. It's not possible to create a subsequence with an empty sequence, right? And everything else is -1, since it's -1, since we don't know the values yet. I'm just giving it assigning the value of -1. It can also be -infinity. Most commonly, people just put -infinity or whatever, just because it's the smallest number or whatever. So yeah, we initialize this 2D list. Now with the 2D list, now what? We either loop through and do a comparison between two sequences. Compare the very last letter in the sequence. So I have it so that I add whoops, let me just change something. I have it so that each letter that we added here, this is the letter we're adding to the sequence. So we're starting with an empty sequence, then we add 1 to the sequence, then we add 4 to the sequence, and that's what I'm trying to present here. And we just check each letter or number we add to the sequence, and wherever we search. So let's say we add a 2 and a 2 onto the sequence, and we also add a 1 to the onto the other sequence, and we just check, hey, is it the same? Because if it's the same, that means we can create a subsequence, a common subsequence, since they both exist in both sequences, and we can create a subsequence since it exists. This thing exists. And we increase the common subsequence by 1. And if you take this letter, you would add 1 to the length if you both didn't take the letter. So the previous value would be so let's say we added this value here and this value here, all right? Or actually the one that makes the most sense is whoops, why can I not erase? Can't seem to be able to erase. Let me just undo. All right. Whoops. So we have, let's say so actually it makes much more sense if we look at this 2 here and this 2 here, all right? And that this only happens at this point, right? Since if we have like this x coordinate here and this y coordinate here, this y coordinate here, right? We look at this value and we just check, okay, if we didn't add these two letters, the previous point would just be here. We're looking at this value. So this is the value that if we didn't add the 2 from this point, and we didn't add this 2 from this point, right? So if we didn't add a 2 from those points, then we just look at what we had before. And beforehand, we had a common subsequence of 0. So if we added those 2 letters, I guess, we would increase the common subsequence by 1. So we just look at the previous point and just add 1. So that'd be 0 plus 0, 0 plus 1, and that'd give us now a common subsequence of 1. Does that make sense? Does anyone have questions about that? Now, what if we compare both letters and numbers and they don't match? So let's say we had, we're doing comparison of, of 1 and 2 here, right? We look at this and we look at this and we're like, oh, 1 and 2 are not the same letter or number. What do we do? Well, we just look back and see, okay, if I added this 2, someone has their mic unmuted. If we look back and see, okay, if we add this 1, it doesn't match. If we add a 2, it doesn't match. So before it, whichever letter we added first, whichever letter, had a longest common subsequence before, like, so let's say if we added a 1 to that first sequence, or we added a 2 to the other sequence, which one, if we added them to the sequence, created the longest common subsequence before it? So we just check, hey, is this value before, the longest common subsequence, or is this value here before the longest common subsequence? And we just take the maximum, all right? So let's loop through and check. Let's find the longest common subsequence. So here, we compare 1 and 2, right? In this case. Well, they're not the same. They're not the same letter. So we just look back. Which number do we add first to get the longest common subsequence? Well, they're both 0, so we just take the maximum of both, so that's 0. 2 and 4, same thing. They're not the same letter. We take 0, 0. We take 0, since that's the longest common subsequence. 3, same thing, that's 0. 4, same thing, 0. And then once we reach the end here, 2 and 2. They're both the same. So we just look at, what if we didn't take what if we didn't take both 2's? And we look back. If we didn't take both 2's, that'd be 0. We add 1 to that subsequence length, so that would be now a length of 1. All right. Next thing, we look at, whoops, why can I not move my, let's say we look at, values of 1 and 1 and 1. All right, 1 and 1. They're both the same letter. What if we didn't add both 1's? Well, that'd be a 0 here. Whoops, why can I not? What if we didn't add the both 1's, I guess, we'd have this value here of 0 here. All right. So if we add both 1's, we just add 1 to the common subsequence. So now this would just be 1 as well. And then we loop through 4. Okay, 4 here. We compare which side has the longest common subsequence before it. Well, it's this 1 here. So we just take the maximum. So far we only know that the longest common subsequence between sequence of 1 and 4 and the sequence of 2 and 1 is only 1. All right. Same thing if we look at 3, the longest common subsequence that we know so far is 1. Look at 4, longest common subsequence is 1. And then 2 here. They're both 1, so we can just say, oh yeah, longest common subsequence is still 1. All right. Now 3, we look back and say, okay, which 1 and 3 are not the same number. So we look back and see, which letter do we add first to get the longest common subsequence? Do we have a sequence of 2 and 1, or an empty sequence? Or a sequence of 2, no, 2, 1, 3, and an empty sequence, or 2, 1, and 1? Well, 2, 2, 1, and 1 have the longest common subsequence of 1. So we take that as the longest common subsequence. Then we look at the next value. 4, same thing. We take whichever has whichever letter we add first to get the longest common subsequence. So that'd still be 1. And now 3 and 3. Okay, 3 and 3. They're both the same letter. We just look back. If we didn't take both letters, then what's the longest common subsequence? That's 1. Now we add 1. So we look back here. Longest common subsequence is 1. We add 1. That gives us 2. And now every other value, okay, maximum between 1 and 2, that's 2. And maximum between 1 and 2 is 2. All right. And now we have the longest common subsequence between this sequence here, so the first sequence, and this sequence here. All right. And now the answer is this very last value here. And that's the last thing we search for. So now once you have this list, you can take the last value, and that's the longest common subsequence. All right. Does anyone have questions about that whole thought process? If not, I'll proceed on. Okay. So let's create the code for this. So first, you need to take input for the two sequences. So in this case, I'll be taking strings, unlike what the question asks you, which is numbers. Either way, it's fine. If you just have to change it up a bit if you're taking numbers. All right. Next, we need to initialize the 2D list that keeps track of the longest common subsequence from sequence 0 to x and sequence 2 to y. So you create the list, and I just set it to all -1 for j in range of the length of y plus 1, since we also have to keep track of an empty sequence, and then for I in range length of x plus 1, so that's keeping track of a common a sequence of an empty sequence. All right. Next, we loop through each cell of the 2D list. So the same thing we did before. So we're looping through each cell of the 2D list. All right. Now, we put the logic inside of the nested for loop. First, let's put the logic of taking nothing from either sequence. So if we have an empty sequence, so this is at I equals 0. So, whoops, this is a bit cluttered. So let me just clean this up. This is at I equals 0. And let's say this is at j equals 0. Right? If it's I equals 0 or j equals 0, that means this, whatever this cell is by default 0, since we have an empty sequence. All right. So we just set it to 0. Now, next, let's put in the logic of what if we can take both letters from each sequence? We need to see, so we need to check, hey, is x at I minus 1, equal to y at j minus 1? And if they're not the same, if they're the same, then we can add this common subsequence from not taking the letters, which is stored at dp at I minus 1 and j minus 1, right? So we're doing I minus 1 plus j minus 1 because in this case, just because we're adding an empty sequence before, we shifted over the indexing to 1 index rather than 0 index. So empty would be 0, and then the first letter would be 1, the second letter would be 2. Rather than in before with dynamic programming, with other questions, we'd start with the first letter at 0, 1, 2, and so on and so forth. So we have to do I minus 1 and j minus 1, right? Now, and we just look back at the previous, previous common subsequence if we didn't take both letters, and we just add 1, all right? Now, if the letters aren't the same, then we just need to see which letter had the longest common sequence before the other character. Which letter did we add first to get the longest common subsequence? If I added, let's say in this case, if I added, a 1 first, if I added this 1 first here, so in this case, let's say we're looking at, this cell here, right? Now this cell, I can either add the 1 to this first sequence or add a 3 to this other, the second sequence. Now, if I added the 1 in the first sequence, I get a common subsequence of 1 because that was the, that was going on in the whole explanation, right? Now, if I added a 3, I have 2, 1, 3 or this empty sequence. That just gives us a common subsequence of 0 since, having an empty sequence gives us a common subsequence of 0 by default. All right. So it's much more preferable if you added this 1 and just so you check back and see. All right. whichever letter we add first gives us the longest common subsequence. We'll take that value, right? So we just look back and see dp at I minus 1 at j, or and dp at I j minus 1, and just take the maximum of those two values. All right. And finally, once we filled in all the values in the 2D list, and we know the longest common subsequence between these two sequences, we can just print the last value stored in the 2D list to get the answer. All right, and that's how you get the answer for this question. Does anyone have questions about that? Because if not, we'll move on. Now, the longest common subsequence question is the most, I guess, confusing one that I even had trouble with. Every other question that I'll take up so far, it's a bit more simpler and easier to understand. So the next question is.
What is? Can I have a question?
Oh yeah.
I don't know if you already explained it because I maybe just dozed off. But what is max supposed to do?
So max pretty much gets the maximum of any two numbers. So in this case, we're looking at the maximum between taking one letter in the sequence or taking another letter in the other sequence. And whichever. So let's say, okay, if I populate this 2D list again, if I zoom in, this was 0, and this was 1. All right. Now, are you saying like what this part does, or like just the whole like max? What does the max function do in Python?
I just asked for the function because I wasn't familiar with it.
Oh, so what the function does is pretty much like, okay, what's the
It just
which value is
adds
the
them
larger?
together.
No, it's which value is the largest, pretty much. So like,
Okay.
let's say I put in max 10 and max 2. Which one's larger?
I'll just put out the larger number.
Yeah, it would print out 10. So it is return you 10. So that's what max does. It's pretty much like, okay, so like if we have like a equals like 10 and b equals 2, max is pretty much just a function where it's like, okay, return, like if a is greater than b, return a. If b is greater than a, return b. And that's pretty much it. That's pretty much what the max function does. It just returns the largest number. Does that make sense?
Okay, thanks.
But yeah, that's pretty much longest common subsequence. Now, next on is longest increasing subsequence. Now, the longest common subsequence problem. Okay, that should be longest increase. Whoops. I didn't really fact check this before. Longest increasing subsequence problem is a problem to determine a subsequence that consists of numbers in increasing order. So like, if we're given like numbers such as 1, 2, 4, 3, 8, -1, 0, right? We just need to find a subsequence that is increasing, that's in increasing order. So in this case, it would be the longest increasing sequence would be 1, 2, 4, 8, and another increasing subsequence would be like 1, 2, 4, 1, 2, 3, and so on and so forth. But like a subsequence that isn't increasing would be like 1, 2, -1, 0, and it has to be strictly increasing. So you can have 1, 2, 2 or something like that. That's not allowed. So let's say we're given this sequence here. All right. The approach of this question is you would just have to look back and see, can I add this number to some subsequence I found earlier? So we have to keep track of the longest common subsequence if we add this number to whatever list, I guess. And if so, then you would add 1 to the length of the subsequence. All right. So we don't have to keep track of the subsequence we're making. For these questions, the question I'm assigning won't have you finding the actual subsequence. You just have to find the length of it. And pretty much each value, I guess, in this list just keeps track of what's the longest subsequence that ends with whatever number. All right. So in this case, like in this list, okay, the longest common this keep tracking of the longest common subsequence that ends with a 1, the longest common subsequence that ends with a 2, longest common subsequence that ends with a 5, and so on and so forth. All right. And we also need to keep track of an empty sequence in this case as well. And since by default, the longest common increasing subsequence in any sequence that isn't empty is 1. Since by default, if we just have one number, that's still an increasing order. All right. So we have this list that keeps track of the length of the longest common subsequence that ends with whatever number. All right. So now what you need to do is loop through each value in a sequence and then look back and be like, okay, is this number greater than whatever previous number before it? If so, that means I can add this number to the end of that subsequence. All right. And make it a longer increasing subsequence. So let's say you have some number at sequence I, and it's greater than some number at j. You just set it to like, okay, you look back at the longest common subsequence at j and say, okay, I can add 1 to it if I add this number here that's strictly increasing. So you look back, add 1, and just set that to the current value. So that might sound confusing, but let me just copy this list down, right? So let's loop through. Okay, so first let's look at the subsequence that ends with 1. Well, before it, there are no numbers you can add to it. So by default, it's 1. We can just end it with that. Now, the number 2 here, all right? Well, we look back, okay, and say, oh, I can 2 here. That's greater than 1. Okay. I can add to that sequence, to that subsequence before. All right, and that becomes a length of 2. That becomes a subsequence of length 2 now. Whoops. That becomes a subsequence of length 2. Whoops. Whoops. Yeah, that becomes a subsequence of length 2. Now let's look at 5 here. Okay, 5. It looks back. Okay, is 5 greater than the number 2? Yes, it is. That means I can add this to the longest subsequence that ended with 2. All right, and that's 2. So, that becomes a subsequence of length 3. Now it looks back at 1. Is this number greater than whatever number before it, which 5 is 5 greater than 1? Yes, it is. That means I can add this number to the longest common subsequence, which is now 2. Now you just compared whichever value is larger. So the number that you already stored so far, which you just check. Okay, if I add this number to whatever subsequence before, is that going to be greater than the number I know so far? And if so, then I can just update it. If it's not, then don't bother. So in this case, I don't bother since if I add 5 to 1, that gives us a subsequence of 2, and in which you don't bother anymore since the largest subsequence that we know so far is 3. Now we look at 4. 4 is 4 greater than 5? No, it isn't. So we can't add this number to this we can't add 4 to this subsequence, right? Now, and let me check back. 2 is 4 greater than 2? Yes. We can add this number to the subsequence. So the subsequence that ends with 2 has a length of 2. So if I add a 4, that makes the subsequence a length of 3. Now, is 3 greater than 1? 1 is the currently known longest subsequence that ends with 4. Yes, it is. That means we can update it to 3. And then we look back at 4. It looks at 1, be like, hey, can I add this number to the subsequence that ends with 1? Oh, yes, I can. But that's going to make a subsequence that's smaller, so we don't bother. And then the next thing, and so on and so forth. So we look at it, we update it again. So 3, we can add that. We can only add that to, we can make that a subsequence of 3. 6, we can add that to the 5 or 4. So that's now 4 again. 2, we can only add that to the 1. So that makes it a 2. 8, we can add this to the 6. That gives us a length of 5. 1, we can't add that to anything. So that's just 1 still. 0, we can't add that to anything. That's still a 0 as well. That's still 1 as well. A -1, we can't add that to anything. That's still, a 1 as well. And then 5, we can only add that to, the 4 or 3. And that's going to give us a length of 4. Does that make sense? And in the end, to get the answer, you just find the largest number in this whole list. So the largest number here is 6. So the longest common subsequence, longest increasing subsequence here is just it has a length of 6, not 6. I meant 5. Yeah, has a length of 5. All right. So the code. Code is a bit simpler to understand this time. You just get n. So n is the number of integers that you have taking input for, and then you have the array to get all the numbers in your sequence. And then in this case, I'm going to keep track of the longest increasing sequence. You don't have to. You can just loop through the whole list and find an increasing sequence. And this is the list that keeps track of the longest increasing subsequence ending at a certain point. And then we loop through each value here. We can ignore the first value since this first value has something to look back on. And then we just loop through at every number before it and just see if the number we're currently searching at is greater than some number before it. And if so, we just check, hey, can we add to it and to make a larger number? And then I'm also keeping track of the longest overall at the end, and I just print out the longest overall. Does that make sense? Does anyone have questions about that?
It's just like when you have like the input from the user, can you like sort the list and then just
Oh
pop
no,
the last
no,
number?
no, you can't. You can't sort the list. The reason why is because a subsequence has to be strictly in the same order as the user's input. So you can't just sort it, be like, okay, sort and then find a number. Because if you sort it, that makes if you have a already sorted input, that means the longest increasing subsequence is just the length of the sequence, right?
Oh yeah.
So that's why we can't just sort it. We have to actually go through and check. Does that make sense?
Yeah, I think so.
What do you mean you think so?
I don't know. It's just like my brain's telling me that you could just sort the list, but then you can't change the user input. So I don't know.
Yeah, because if you sort it, you just change how the numbers are ordered, right? So you can't change the order that the numbers are coming in. So like,
Okay.
if we have this previous whoops, wrong color. If we have this here, right? This order. If we sort it, that gives us -1, 0, 1, 2, 3, 2, 3, 4, 8. And that already gives us a increasing sequence. So there's no point of searching at all. This is already an increasing sequence, and as such, this is the length of the increasing sequence. But if we have it in like a completely randomized, sequence in random orders, 1, 2, 4 is an increasing sequence. 1, 2, 8 1, 2, 4, 8 is an increasing sequence. But 4, 2, 3 is not increasing, and it's not a subsequence. Does that make sense? Because you can't go back and be like, okay, 4, I'm gonna take that and then take that. No, you have to take it in the exact same order as how it's ordered in the sequence. Does that make sense?
Yeah. Thanks for clarifying.
Yeah. So that's what a subsequence is. It's pretty much, it has to be in the exact same order. Now, the next question, and that's one of the questions that someone asked me, is coin change. And coin change is one of my favorite questions. I kid you not. And this is, well, it's one of my favorite DP questions. I have other questions with other categories. And this is a question where you're given an infinite amount of coins, and you just need to find the minimum number of coins to make a certain amount of money. All right. So, as I said last week, there are really only two ideas you need to take into account with coin change. Firstly, it takes 0 coins to make $0. For obvious reasons, you don't need coins to make $0. If you can't just add $0 coins, right? Other than that, we have no clue how many coins it takes to make X number of dollars. So we just say that it takes an infinite amount to make X dollars. Secondly, let's say you have $5. All right, let's say you have a $5 coin, and it takes you 13 coins to make $45. All right, that so far. But you also know that it takes you 5 coins to make $40. You know how if you just add $5 to the if you add the $5 to the $40 coin pile, that 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 gives you 6 coin. You can carry around 6 coins to make $45 rather than the 13 coins that you know so far, right? You just so it's similar to longest increasing sequence in which you have to look back and see if I add this coin to some earlier pile, is that going to be fewer coins than not taking this coin? So like increasing sequence, we need to have a list starting from 0 all the way up to X dollars we're trying to make. So let's say we're trying to make $18 and we only have the coins of $1, $3, and $5. Or $5, all right? Initializing the list would look like this. Since we have we start with 0, since it takes $0 to make 0 coins. No, it takes 0 coins to make $0, and every other value is some unknown number. I just have the question marks. The question marks in your code should be some arbitrarily large number to represent an infinite amount of coins. So since we don't really know how many coins it takes, it could be a billion, trillion, gazillion, who knows, you know? And let's fill in if I only had a $5 coin, all right? So let me just copy this. Let me just copy this code here, this list here, all right? Now, so the reason why I have it like this, so have it filled in like this. Let's look at this, all right? Let's look at this code, and let's say we have this first. Let's have this $5 coin, all right? Now we can't make $1. We can't make $1 with a $5 coin. That would be that's too large. So we can ignore 1, 2, 3, and 4. Now let's look at 5. All right, 5. We look back. If we didn't take this $5 coin to make $5, that'd be $0. All right, and it takes 0 coins to make $0. If I add 1 coin, add this $5 coin, it's now 1 coin to make $5. Is that lower than some arbitrarily large number? Yes. All right, that means we can update this value and set it to 1. 6, we look back, okay? We add 1 coin to some arbitrary large number to make $1, to make $6. So we have one arbitrarily large number plus 1. Is that greater than another arbitrary number? No. Arbitrarily large number plus 1 is more than some already arbitrarily large number. It's like, okay, just to make it much more simpler, let's say the arbitrary large number is 100, all right? And now it takes 100 coins to make $1. If I add 1, that's 101. And we already know for 6, it takes 6. It takes 100 coins to make 6, and that's also an arbitrarily large number. So is 101 less than 100? No. So we kind of just ignore it. 7, same thing. 8, same thing. 9, same thing. 10, okay, 10 we look back. At $5. All right. $5, it takes one coin to make $5. So if I add a $5 coin to if I add a $5 coin to $5, it now takes takes 2 coins to make $10. If I add a $5 coin to how much coins it takes to make $5. All right, and now 2 less than some arbitrary large number. Yes, 2 is definitely smaller than some arbitrary large number. And then 11, 12, 13, 14, same idea. You can't add 1 to an arbitrarily large number and expect it to be less than already an arbitrarily large number. Now 15. 15 is the same idea as 10. Okay? If we add whatever it takes to, so let's say it takes 2 coins to make $10. If I add a $5 coin, it takes 3 coins to make $15 now. Is 3 coins for $15 better than some arbitrarily large number to make 15 coins? Yes. Okay, we can update it now. Now it takes 3 coins to make $15. 16, 17, 18, same idea with before. You can't add 1 to an arbitrarily large number and expect it to be lower than already an arbitrarily large number. Now next, let's add a $3 coin. All right, $3. $1, $2. You can't add a $3 coin and expect to make $1 $2. You know, that's not possible. $3. Okay, $3. So far, we know it takes an arbitrarily large number to make $3. But I look at $0. It takes zero coins to make $0. If I add this $3 coin, it now takes one coin to make $3. One coin is better than some arbitrary large number. We just, okay, we set it to one coin. Four, we can't add one to an arbitrary large number to make $1, since we don't know how many coins it takes to make $1. So we can't solve for 4. 5, we can't solve for 2. So there's no point of searching for, again. Now 6, okay? It takes one coin to make $3. All right? That means there's no point of search. There's no point, it takes an arbitrarily large number to make $6. And it takes one coin to make $3. So if I add a $3 coin to that, that makes 2 coins to make $6. 2 versus infinity. You do take 2, all right? And then let's just keep looping that. 7, we don't know. 8, we don't know. 9, we can just say, all right, that's 3 now. 10, we don't know. 11, we don't know. 12, we can just say 4. 13, we don't know. 14, no. 15, all right? Now it takes 4 coins to make $12. If we add a $3 coin, that makes 5 coins to make $15, all right? Since we add a $3 coin to $12, that makes $15. And adding a coin, it takes 4 coins to make $12, and adding one coin makes it makes it 5 coins. So, but we already know it takes 3 coins to make $15. So, 5 coins versus 3 coins. I think I'd prefer the 3 coins that we already have so far. So we don't have to update the current value. 16, we don't know. 17, we don't know. 18. Now 18, we look back and be like, okay, $3 before it was $15. And it takes 3 coins to make $15. All right? If I add 1, that's 4 coins to make $18. If I add the $3 coin, it makes 4 coins to make $18. Is 4 coins better some arbitrarily large number? Yes, it is. Now we update it, and now it takes 4 coins. And then we add the $1 coin. The $1 coin, we just loop through, and it fills this whole thing. So if I loop through again, with the same mindset, 1, that says it's 1, 2, 2, 3, we don't change. 4, now it's 1, 5, 6, 7 is 3, 8 is 4, 9, 10, 11, 3, 12, 4, 13, 5, 14, 6. Oh, wait, whoops. Did I do something wrong? If I add a 1. I think I put in my values wrong. 15 should be 3, 16 should be 4, 17 should be 5. Yeah. Oh, this should be right. 12 is 4, 13 should be, 13 should be 5. And 16 should be 6. All right. And that's how many coins. And then we just look at the very last summary and see, okay, it takes 4 coins to make $18. All right. Simple. Any other questions about the whole approach? No questions. All right. So code, first we need to know how much money we're trying to calculate for. All right. So we take total money. And then next we need to know the number of coins we're trying to accept and then the value of each coin. All right. So then we need to create a list that consists of arbitrarily large numbers. No, it consists of the number of coins it takes to make X dollars. And then we need to fill it with some arbitrarily large number, except for 0, since it takes $0 to make 0 coins to make $0. All right. Now we need to loop through each individual coin and each individual dollar to compare and see if we can add this coin. Nope, we can just skip to the starting dollar amount since we know we can't add this coin before the starting value. So we can't add $5. We can't add a $5 coin to know how many coins it takes to make $4. So we can just jump straight to $5, all right? And we just check, hey, is the number of coins we know so far less? We'll take the lowest number between the number of coins it takes to make X dollars so far, or X dollars minus the denomination we're looking for. So like, if we're looking at 5, how many dollars, how many coins it takes to make make $5 with a $5 coin. We look at $5 minus the denomination, which is minus 5, which equals 0, and just see if we add 1 coin to that, is that better? Is that less than how much we know so far? Let me just update our current value with that, and then we just print the very last number, since that's the number of coins it takes to make that much money. All right, does that make sense? If anyone does anyone have questions about that? All right. If not, then we can move on to the very last uh, dynamic programming question. The last and probably the most important dynamic programming question so far is knapsack. The knapsack problem, I guess. The question is similar to coin change. However, rather than trying to minimize something, we're trying to maximize some value that we don't know. Also, rather than having unlimited coins, we are only limited to taking one item at a time. So I guess the most common scenario I'd say for the knapsack problem is, let's say we're given multiple items consisting of differing weights, and let's say it has like some sort of value associated with each item. Let's say it's like some sort of sentimental value, I guess, to each item. And you can only carry a certain amount of weight, but you can also carry any number of items. You know, this knapsack is a really big knapsack, but you can only carry like a limited amount of weight. What is the maximum value? What's the maximum, like, what the maximum with all these items? What's the most value you can get out of carrying uh like some arrangement of these items? So there are many ways we can need to consider with this approach to this problem. Firstly, taking like, you know, with coin change, taking no items results in 0 value. Your bag has no value, unfortunately, so you get 0 value if you take nothing. Secondly, you need to keep track of each item you take and compare. And see, if I add this item to the previously so let's say I add item 1, and I'm looking at if I can add item 2. You need to look back and see, okay, what are values with adding item 1, and check, okay, is adding item 2 compared to item 1 better than just what I had before, right? Or, and like, let's say you also need to keep track of like with coin change with weights or and such. So let's say I had an item of weight 5, whatever, right? And just see, okay, with weight 5, if I add this item to like whatever weight, you have to look back at before adding this weight and looking at that value, right? And just seeing, do I get more value if I add this item with this weight, right? Now the approach is different from coin change though. We need to create a 2D list instead of a 1D list. So the 2D list first has the same length as coin change, where it's the maximum weight you can actually take, plus 1 for taking 0 weight. However, the height of it should be the number of items, plus 1, since we need to consider for taking no items. All right. So let's say we have 4 items, and you can only carry a maximum weight of 6. So the 4 items are like has a value of 5 with a weight of 4, a value of 4 with a weight of 3, value of 3 with a weight of 2, and a value of 2 with a weight of 1. I'm going to copy this so that I can have keep track of it in whiteboard. And now we need to create a 2D list of 7 by 5 in this case, since, you know, we can take a weight of 6. We can only take a maximum weight of 6. All right, and we're carrying 4 items, so we need to keep track of taking no weight and no items. In this scenario, each row is the item you could potentially be added to, that could potentially be added to the knapsack, and each column is the maximum weight you can take. We can fill the 2D list with 0, since that's the minimum value you can ever have with that's a minimum value you can ever have with a knapsack, since taking 0 items results in 0 weight. So we'll just set everything to 0, since taking nothing would just have no weight value to it at all. So similar to coin change, you would look back as if you didn't add the weight of each individual item. But unlike coin change, since this is a 2D list and you're only able to add each item once, you need to look at the previous row rather than your current row, I guess. So the previous row is everything before you add this item. So in order to actually know of the value before adding this item, and since you can only take this item once, you have to look at the previous row, which is before you add this item. So let's say you're currently looking at a knapsack with a maximum weight of 4, and you're trying to add an item of weight 2, all right? You need to look at the previous row at weight 2 plus the value of the item. So let's say, okay, if we're looking at this, this grid, this 2D list here, sorry if it's a bit confusing. Let's say we have looking at item 1 or item 2, right? Here. And let's say this item 2 has a weight of 2, right? And we're looking at the max, if it had a maximum weight of 4 here. We just look back and see, okay, before we add this item to get to a weight of 4, we had to have a weight of 2. Now, if I add this item before with a weight of 2 to whatever value it is, so in this case, it would be some value here, to weight to 4 here, is that going to be greater than not taking this item at all, which would be whatever was previous? Does that make sense? If anyone is confused or has questions about that, feel free to interrupt. All right. So we have that idea throughout the whole list. So throughout the code. So let's fill the first item here. All right. So with item 1, okay, from 0 to 4, we can't take it at all. That item is going to exceed the maximum weight of our knapsack. So that's going to be by default 0. Oh wait, no, it has a weight of 4. So from 0 to 3, never mind. At 4, we just look back and see, okay, before we add this item, at weight 0, if we add this item, we just look back before adding this item and before adding the weight of this item, we just see, okay, what's the value then? We add the value of this item as if we were going to take this item. So that'd be plus 5. So plus 5 in this case. And just check and compare, hey, is the value before taking this item at all? And completely not taking this item better than the value of actually adding this item? Well, it is. If we add this item, we have a value of 5 as opposed to 0. So we just set it to 5, and then same thing with this number, with a weight of 5 here. We look back at a weight of 1 and just see, okay, at a weight of 1 and taking nothing, is that if we take our current item, is it better than not taking it at all? Yes, it is. Okay, we can add, we set it to 5, and same thing with 6 here, all right? Now 2, we take the same philosophy with 2. So with 2, 1 and 2, with weights 0, 1, and 2, maximum weight of 0, 1, and 2, we can't take it at all. We can't take their current item, all right? So we just have to take we have to ignore taking this item. So we just take the previous value. So we 0 would drag down here, 1 would drag down here, and 2 would drag down here. Now 3, we look back at only taking up to item 1. Now, before adding this weight of this item, that's 0, right? Now at item 1 and 0, and adding up to item 1 and adding only up to a weight of 0 has a value of 0. Now we add this item. We added a weight of 3. Now our knapsack will have a weight of 3. That means we also have to add the value to the knapsack. And we just see, okay, if we add this item, is this value better than not taking this item? Well, it is. It is better. So we just update this value to 4, since that's the value of 4. That's the value of adding this item. And then with 4, same thing. That would be 4. 5, that same thing. It would be 4. Oh, wait, no. Actually, with 4, we just look back. Okay. Should we add this item? No, we shouldn't. Because before, we had a value of 5 by taking the previous item. So that means it's better. We're better off just taking the previous item. So we have a maximum weight of 5, maximum value of 5, maximum value of 5 here, and a maximum value of 5 here. So there's no point of taking the previous item since we're not getting any value. No, we're not. We shouldn't take the current item actually, since we're not getting any value. We should just take the previous item since the previous item gives us more value. All right. Now we move on to item 3. So we ignore 0 and 1 since that has no weight. We can't add this item with a maximum weight of 0 and maximum weight of 1. So we just take the previous values, I guess. Now, weight of 2, we just look back, see, hey, is it better? Are we better off adding this item? Yes, we are. So we have a weight of a value of 3. 3 here, same thing. We look back at this point here, and that's better than. Is that better? Is 3. So if we add a value of 3 here, is that better than the 4 below before? And if we didn't take this item, yes. If we like not taking this item is better than taking this item. So that will result in 4. And then here with 4 here, we look back and see, okay, this is nothing. That if we take this item, we get a value of 3. Is that better than not taking this item, which is 5? Not taking this item is better. So we set this 5, and then with here at 5 here, now if we take this item, we have 4 plus the value of this item, which is 3, which gives us 7. So 3, that gives us 7. Now, is 7 greater than 5? Yes, it is. 7 is greater than 5. Then that means we can't take this item with item 2. So, we have a value of 7. And then we look back at 6 here. 6 with a maximum weight of 6. Should we take item 3? Yeah, I guess. Because before, we take item 1, which has a maximum weight of 4, which has a weight of 4 with a value of 5. And then we add item 3, which has a weight of 2 and has a value of 3. So that creates a weight of 6 and has a value of 8. And that's better than all we know so far. So that's our maximum value. And then we fill the same philosophy in number 4 with item 4. And that gives us 2, 3, 5, 6, 7, and 9. All right. So our code. So we start with the maximum weight you can carry, number of items you can carry, and all the items, I guess. So I have it so that it has the order of value, then weight. Depending on the question, it might be other way around, right? Next, we have to create the 2D list of zeros that consist of the maximum value you can have for each item and for each weight, maximum weight, I guess. So I have the maximum weight plus 1, since we need to account for taking no weight, and plus 1 for items, since we have to account for having no items. Then we just loop through each item, then through each weight we're searching through. So we search through all the number of items, and we search through all the number of weights, all the weights in here, all right? Now we need to implement the actual logic for this question. First, we can just take the previous value if we didn't take the item, our current item by default, we can just set the, lower each value by 1 and we'll pushing all the values from the previous row onto our current row by default, since that's the idea of if we didn't take any items from the previous, if we didn't take our current item that we're looking for, right? And then we have to see if we can actually take the current item we're looking at, then compare, is the value we currently have now from not taking the item less than if we were to take this item from the weight before it and the item before it, all right? So here I get the previous value, so that'd be knapsack at I plus 1 at j equals knapsack at I j. We're counting from 0 in the for loop, but the 2D list starts counting the items from 1, so as we have 0 as taking no items, all right? And then we check, okay, so here is j, so j is the maximum weight of each column, I guess. Is that greater than the item, the item's weight? Because if so, that means we can take this item with maximum weight of this knapsack. And we just check, okay? We look back. Is our current, number we have so far, the current value so far, better than not adding this weight of this item and not adding this item in general. So we look back at the previous row, which is not taking this item at all, and we look back at similar to coin change, where we subtract the weight of this item, and then we add the value of this item to denote the new value. And then lastly, after we run through all that, we just print the last value, since that's the very last value. That's the maximum value you get from the knapsack. All right. Does anyone have questions about that? That sounded a bit confusing, and I did stutter a bit. So, if anyone has questions about that, feel free to ask. If not, then we can move on. So that knapsack question is known as 0-1 knapsack. So that's saying that you can only take 0 items or 1 item. Now, another type of knapsack question is an unbounded knapsack. So this type of question is more close to coin change than the previous knapsack I just showed you. So rather than being limited to 1 item, you can take an infinite amount of items. In this case, you would use a 1D list instead and look back in the same way as coin change. So you look at the weight at a certain point, the maximum weight at a certain point, and just subtract the weight of that item, and you look back that way. So similar to a coin change, where you look back at the minus the denomination, right? And you'd take but rather than adding 1 like coin change, you'd add the value of the item similar to knapsack, and you'd also take the maximum item similar to knapsack as well. And you have the same principle of having 0 value for taking absolutely nothing, though. Now this is a bit different though. So rather than looping through each item in the outermost loop, like coin change, or a knapsack, you loop through the maximum knapsack weight first, then each item. And it's pretty much coin change. It's really similar to coin change. So so you still take the input the same as knapsack, but instead you create a knapsack with a 1D list that consists of 0, since that's the minimum value you get for taking nothing. And then you just go through each weight and then each item and see if you first take the item, then check the value of you first go through each weight, then each item, and see if you can first take the item. So similar to how similar to how in knapsack before, where you have to check if the weight exceeds the current value, I guess. And then just check, okay, then add the value of that item and compare it to the current value that you know so far of the maximum knapsack. All right. And then lastly, like all other quotes, you just print the very last value. All right. Does that make sense? Oh, I forgot to add the checking part. I'll update that on. I can just quickly add that. So like if j at 1 is greater or equal to I, all right? And let me just format this. So if I format this, and I copy and paste, all right. And that's pretty much all you have to do for knapsack here, for unbounded knapsack. All right. Does anyone have questions about that? If not, then we've pretty much reached a conclusion for dynamic programming. So like with most other questions, you will not encounter these questions as is directly like this. I guarantee you'll have to manipulate your answer in a way to get the proper solution. So expect that. And these questions aren't even standardized at all. These are just a generalization of dynamic programming questions. And there are so many variations of these questions as well, with optimization that go along with it. But however, the code I showed you so far will get you started with learning more advanced programming algorithms. However, don't let that put you down from dynamic programming. Dynamic programming is more or less a thought process that will take time. I personally didn't get it until 2 years after I started competitive programming, but as long as you practice, you'll definitely get there. So the questions I have so far that I assigned you guys, there aren't many questions to add for dynamic programming. You should still try to DP questions from last week if you haven't finished them. I also put some I put the wrong questions that I thought were easy first. So here are some better questions you should try first. So coin, change, and golf. And then here are some additional questions if you want to try, and they're a bit tricky. All right. And I guess we've reached the conclusion for CS Club Junior, right? And that's a wrap. And that's all you need to get started for CC Junior and what you need to get started with Senior CS Club. And many of you guys came to CS Club without any knowledge of computer science or programming. And look at you guys. You guys came a long way. 13 weeks. 13 weeks of computer science, and you guys already are doing dynamic programming and graph theory. And yeah, that's pretty much the end of it. And all my lessons are available on YouTube if they're uploaded at watch.vmcs.club. And all the lesson plans are also available at go.vmcs.club slash 2022 junior lessons. So that's pretty much it. That's pretty much it for Junior CS Club. Does anyone have questions at all? No questions? All right. Then I guess we can. Oh, someone's typing. Two people are typing. Three people are typing. All right. Uh, all right. Yeah. So if there are no questions, then I guess I can end. We can end here. So yeah. So thank you for joining me on this journey for CS Club. You'll once we're done the CCC. I'm if people vote to learn web dev or Git, then I'll still be teaching that. But if not, then I'll probably do another thank you, a closing remark at the end of the year. But yeah, thank you for joining me along this journey, guys. And I hope you guys learned something new this year. And I hope that you guys stick around next year for CS Club Junior, Senior. So yeah, if not, if there are no questions, no more questions, I'm still, I'm still available on Discord and to if you guys need have any questions, feel free to post on Discord, or privately message me. But other than that, thank you guys, and hope you guys have a nice day.